Yeah. All right, so our focus is going to be about arithmetic sequences this time. So sequence is still the same thing. All the notation is the same. The difference is we're going to focus on this one specific pattern that they call arithmetic, and then you can see here the description of the pattern. So it's a sequence where the difference between the consecutive terms is constant. So in our board game that we just played, you know, the two charts that you guys saw, the first two, how they had a consistent thing happening, +3 or -2, and the rule turned out to be linear. That is what an arithmetic sequence rule will look like. Okay? The third one that we did didn't work that way, and we had a quadratic as our rule. Okay? But that's because it didn't meet this requirement. Right? And then that difference that we saw between the terms, the +3 and the -2, they call that the common difference. It means constant difference. So anytime you hear that terminology, you know that they're talking about an arithmetic sequence or series and that kind of recursive thing, like what's happening between each term. You know, are you adding 3 to get to the next one? Are you subtracting 2 to get to the next one? And that's the difference. And then for the difference, they use the letter D. Okay? So when you see D show up in formulas, you know that it's just about the difference. I'm laughing. All right, I'll give you guys a second to copy it down. All right. Before we actually start example 1, notice it says it gives you a term of the arithmetic sequence. It tells you that the D is equal to -7. And then it says to write the rule. When they say write the rule for the nth term, they're talking about the explicit rule. So we're looking for our answer to be something like this, where someone can just have an expression on the other side. They can plug in n and get the answer they're looking for. Okay, which number would be in the sequence at that certain spot. So because arithmetic sequences have a special pattern, it actually works out that you don't just have to guess and check all the time. Okay? Like the silent board game, you guys started seeing a pattern, and then that pattern helped you quickly come up with a rule. So what we want to do is kind of establish what's happening each time. So you don't have to write down the part as I'm describing how we get the rule, but then you're going to want to write down what the actual rule is. Okay? So I'm going to take one of the sequences that we looked at on the board. So we had something like this. I'm starting it with our input of 1 because I'm making my sequence starting with 1. What would come next in this sequence? 14. And then 17. Okay. Okay. So you know this because you found the common difference, and the common difference was 3. Okay. So a recursive rule for this would be take the term before and add 3. Right? That would happen every single time, and that would work. But to write a rule for the nth term, we want our explicit rule. Okay? So let's think about what's happening to get from term to term. We've already established that recursively, or how to get from one to the next, we're adding 3. Okay? But if we want to make this about n, we have to somehow relate all of this information to, like, if I want the 10th one, what do I do with that 3, you know, if I'm at the 10th term? Our first term is not going to change. It's just our first term. Okay? Even in a recursive rule, you need the first term because it's the beginning that you started doing that whole adding 3 thing to it. Okay? So our second term, which would be the 8, okay? Let's think about how we get 8 as our second term. So to get 8 from the first term, what did we do? We just added 3. Okay? So it is the second term, but here's another way to write it using just the first term. Okay? Then we look at the third term, okay, which is 11. Now, what's another way that we could write it instead of writing it third term? What's kind of a more formulaic way we could write it? Go ahead. So 3 times, okay, good. So it's like you took the first term, right? And basically we added 6, okay? But I like the way that he said it. He didn't just say add 6. He said 3 times 2, okay? Because it's not just add 6 because 11 is 6 bigger than 5. It's add 6 because you added 3 once, and then you added 3 again if you were trying to get to the third term. Does that make sense? So I'm going to write it the way that he said it. I'm going to write it as this is the first term, and the only reason that it's 6 is because our difference was 3, and I had to use that twice to get to the third term. Okay? All right, so what about skipping over here to 17, which is the fifth term? Okay? You would use the first term plus, and you could go, well, let's see, 17 minus 5 is 12, so I'm adding 12. But that doesn't really help me that much. Okay? Why am I adding 12? Yes? Because I added 3 4 times. I started at the first term and I added 3. I added it again, and again, which was a total of 4 times that I added 3. So to get this fifth term, I took the first term and I added 3 4 times. Do you guys see a pattern forming in the way that we're writing this? Okay. So to get any term in our sequence, would you guys agree that it's all going to be based on at least having the first term? Okay, that's how we rewrote them. And then in this specific instance, they're all going to add some amount of 3s. Okay? But then the question is, how many 3s are you adding? Can anybody think they can kind of sum it up into what it's going to be? Yes? Yeah? I don't know everyone's name. Good. N minus 1. So why is he saying n minus 1 instead of n? So like if I wanted to find the 10th term, I'm going to take the first term and I'm going to add 3 to it. How many times? 9 times. Okay. Why not 10 times? Good, because then we'd have the 11th term because we started already at the first term, right? So look at the pattern. To get the second term, I only added 3 1 time. To get the third term, I added 3 2 times. To get the fifth term, I added 3 4 times. You're always adding that difference one less time. Does that make sense to everybody? All right, so the formula, if we're going to make a general formula all the time for these arithmetic sequences, they're all going to look like this. The only thing that's going to change is that it's not always going to be determined by plus 3, right? Like the other one we had up on our board was like a minus 2 was the constant difference between the terms. So if I want to write a general formula, I can't put 3 in it. Not every sequence I ever write is going to depend on 3. But what variable did we use to represent what 3 is in this problem? D as the common difference. So I'm definitely going to be using D, the common difference. I'm definitely going to be using the first term. And where is this coming from? N? N minus 1. Good. It's 1 less than what we were looking at, right? So this is about where you are in the list, okay, the N position, but we're always using 1 less. Okay? So our general rule, anytime we're working with an arithmetic sequence, because it's going to follow this same procedure, is that an explicit formula would include the first term plus n minus 1 times the difference. But do you guys see where they got that formula from? Somebody didn't just make it up out of thin air. It's because every time you're using an arithmetic sequence, this same thing's going to happen just with a different number right here in this spot. So you're going to see this same pattern happening over and over again. Marlon? In this one, we can switch A1 for 5. So let's talk about that with the example 1 that's up here. Okay? So what he's saying is, can we switch A1 for 5? If we were writing an explicit formula for this sequence, yes. A1 would be 5, D would be 3, and then we would have a formula where someone could just plug in n and get whatever they want. This is kind of like the general rule for any arithmetic sequence. You can use this to kind of construct what you want to write, okay? Because they're all going to behave the same. So if we look at the example that we have up here, our first example, why don't we go through and look at how we would solve this problem, okay? So one term of an arithmetic sequence is A7 equals 15. And on the slide, the 7 is not a subscript, but it should be, and it is on your note-taking guide, right? And then it says the common difference is negative 7. Find the rule for the nth term. So my ultimate goal is to write something like this, where just like Marlon said, I can actually replace the A1 and replace the difference with the values that they are for this example, okay? So we know 2 things. We know that A7 is 15, and we know that D is negative 7. Okay? So if I'm going to write a rule for this arithmetic sequence, I know I want an to equal, and I want to come up with that formula where they can just plug in n. Since they say it's arithmetic, I know it's going to follow the same pattern as this one did. All the arithmetic sequences will. So I know that I want the first term and the difference, and they gave me the difference. So I have the d to plug in to the formula. What I'm missing is that they gave me the 7th term instead of the first term. I would really have liked the first term if I wanted to make the problem really simple, right? Any ideas on how we can get what we need? Yes? Plus 7 times 6. Oh, gotcha. Okay, so you're working backwards. So what he's saying is he knows that there was a list, right? Tell me if I get this wrong. And that at the 7th term, 15 was in the list, and he's understanding that that's coming from subtracting 7 from each term, right? So he's like going to hop backwards. So if you're going the opposite direction, you would be adding 7 to each term. So if you worked backwards, he's saying go ahead and do a plus 7 so that you're undoing it. And if you were going to count backwards to the first term, if this right here is the 7th term, okay, then you would go back the 6th, 5th, 4th, 3rd, 2nd, 1st. So you would end up going back 6 times. Okay? So he's saying eventually I would go back 6 times 7, which would be 42. Okay? But I was at 15, so I'd have to add 42 to that to get the first term. That would work. Okay? Anybody think of another way to get the first term? You could go back through each term if you wanted, right? It's up to you guys. Another way to get it is you could use your rule to help you. Remember that this is an n value, and this is an a sub n value. So those are like x-y pairs that would go into an equation. Okay? I could actually plug those values into this equation. 15 is what I'm getting as a result. Okay? I still don't know what A1 is. But 15 happens in what spot of my sequence? The 7th spot. So the 15 is the AN. The 7 is the actual N number. You're going to notice we're actually going to end up doing the operations that are exactly what he said. Okay? We're going to end up doing 6 times negative 7. Okay? But you guys might be thinking, oh, he said add, and this is going to be subtract. But watch what happens. This gives us negative 42. But if I want to figure out what A1 is, what do I have to do? Add that 42 to the 15. And that's going to give me that my first term is equal to 57. So that's what needed to be here in my rule. And you're normally not going to see them keep the rule like that because that's not simplified. There's something to distribute and there's like terms to combine. Okay? So what you would see them do is you would see them actually take, expand, and simplify the rule. So you guys can do that right now on your paper. So distribute the negative 7 to the n minus 1. And then we should all get the same rule. So we have 57 n minus 1 times negative 7.
Why don't they do a to the 0 so that they can just have n instead of n minus 1?
Yeah. In a sequence, specifically, it's thought that the first term is the first term, not the 0th term. But when we start talking about some equations of lines, we're going to look at what kind of meaning that like 0 term has and how we could use that. It's not to say they never use it. In science, actually, they use 0 subscript a lot as the initial starting point. But because we're counting, n is supposed to represent places, so they only use natural numbers, essentially, for n. So like if you ever solved for n and got like negative 2, that wouldn't work because there's not like a negative 2 position in the sequence. So they just stick with the natural numbers. Okay? I don't know why they didn't choose to do it the other way. All right. Okay, so our rule for this sequence would be 64 minus 7n, or negative 7n plus 64. All right, the next problem that we're looking at gives us two terms, and we're supposed to find the rule and then find an n value when a sub n equals 44. So first of all, to find the rule, think about what we have here. We don't have the first term or the difference, but we have that a sub 7 is the 20th term, and a sub 23 is 52. So I'm sorry, let me re-say what I said before. The 7th term is 20, and the 23rd term is 52. And we know that if we want to write a rule, it says it's arithmetic, so we know it follows this pattern of using the first term, and then it uses the difference several times, exactly n minus 1 times for each term. So if we want to figure out what the rule is and we don't have the first term or the difference, there are some ways that we could just use our number sense and pattern sense, knowing that the 7th term is 20 and the 23rd term is 52, to figure out the missing pieces. If you didn't want to write that out, or it was a little bit difficult for you to see, another way to do this would be to translate each one of these into an equation. Remember, a sub 7 equals 20 is really saying that when n is 7, an is 20. And a sub 23 equal to 52 is really saying when n is 23, an is 52. So after that, we're going to go ahead and use those to kind of help us write equations. Again, this is not the only way. Okay, this is a very algebraic way to do it. There are lots of other ways to do it just with your knowledge of patterns. So an is 20 when n is 7, and an is 52 when n is 23. So this is how this would look in each of those. And neither one is solvable on its own, but together, considering they're about the same sequence, we have a system of equations that we can solve. So if I look at each of these a little bit closer, I really have 20 equals a sub 1 plus 6d, and I have 52 is equal to a sub 1 plus 22d. If I multiply each of these by a negative 1 and then add them together in order to perform elimination on this system, then the a1s will cancel out, and I would have negative 16d equals negative 32, and that would give me that d is equal to 2. So I now have my common difference. I still don't have my first term, so I'm going to take the fact that d is equal to 2, and I'm going to plug it into one of those equations I was using. So I'm going to use the first equation right here. So 20 is equal to a1 plus 6 and then times d, but I now know that d is 2. So this gives me that 20 is equal to a1 plus 12, meaning a1 is 8. And now with both my a1 and my d, I can go ahead and write my rule. So I'm going to go back to that basic arithmetic sequence rule. Use my a1, which is 8, and my d, which is 2. And I'm going to simplify by distributing and combining like terms. And if you ever wondered if your rule is correct, you could go and plug in the given information and make sure that it makes sense. That when I plug 7 in for n, I actually get 20, and when I plug 23 in for n, I actually get 52, and I can have a general sense that my rule is correct for this circumstance. Okay. All right, the last thing that we're going to look at is this problem, and it says the number of seats in the first 16 rows of a curved section of an arena form an arithmetic sequence. There are 20 seats in row 1, 23 seats in row 2. How many seats are in row 16? So I'm first going to write this out like a sequence. Now notice they only gave me the first row or the first term in my sequence, and then the second row or the second term in my sequence. Normally I would have no way of knowing if that pattern continues, but they told me it was an arithmetic sequence. So when I see that to get from the first term to the second term is simply by adding 3, then I know that it's going to continue in that way. And so I would imagine this sequence as adding 3 each time to get there. So then looking at this sequence, if I want to find out how many seats are in row 16, that really means I'm looking for the 16th term of the sequence. Now, I could continue writing out my sequence, but then that's not a good strategy for if I want to find like a really big term, like the 100th term or something like that. So instead, I would really like it if I had a rule where I could find a sub 16 by plugging in 16 for n. So that would prompt me to want to use, again, this rule that we saw that helps us write an explicit rule for the arithmetic sequence. So when we do this, A1 is 20, and the difference is 3 based on the information they gave us about the number of seats in each row. So if we simplify this, and you don't have to simplify because you know what? We weren't actually looking for the rule. We were really just looking for how many seats were in the 16th row. We could have gone on and just done that. So I get that a sub n is equal to 17 plus 3n. So to find a sub 16, I would do 17 plus 3 times 16. Let's see, that would be 48 plus 17, which would be 65. So my answer would be that there are 65 seats in row 16. And that would be it. All right, so this should help you guys with homework too, and then just bring your questions on Monday and we'll answer them. Thanks.